Well, here we are, the last door. Behind this is the last problem.
The last problem?
A problem that combines all three topics throughout the summer.
Winter.
Whatever. The point is, we need to unlock this door somehow.
And the way we do that is by answering a problem, right?
Yeah, and here it is.
Wait, what? Are you kidding me?
That explains all the Riemann hypothesis references this month.
How are you not unfazed by this? We have to prove the freaking Riemann hypothesis to open this door.
Sayo, calm down. Hey look, what's this?
Huh?
It doesn't say we have to prove it, we just have to explain what it is. This series is, at its core, a mathematics explication series.
That's slightly easier.
Alright, let's do this. For the second to last time, this is SoME. The heart of the Riemann hypothesis is, of course, the Riemann zeta function. This is defined as the following sum. Now, I want you to factor this.
How am I supposed to factor this?
Well, let's divide this by 1 over 2 to the s. Notice how now we have all multiples of 2. Subtracting this from the original function, we have effectively removed all the multiples of 2 in the series. We can do the same thing with 3, dividing the function by 1 over 3 to the s. We are left with every number that's a multiple of 3 but not 2, and subtracting from the equation before, we are left with numbers that aren't multiples of 2 and 3.
Wait, this is just a sieve of Eratosthenes. We can do the same with 5, 7, 11, and so on.
Eventually, if you do this with all the primes, you just get 1. Rearranging the equation, you get this. Euler proved this in 1737.
Of course he did.
Anyway, this is the gamma function, a continuation of the factorial function. What happens if we change this x into an sx? Making a u substitution, it's easy to see that you get the gamma function over n to the s. So what happens if we sum this up for all values of n? Well, since integration is a linear transformation, we can put the summation into the integral, use the geometric series, and voila! We generalize the zeta function. Now try calculating this integral.
Well, doing the same thing as before, we end up with this, and we can put a summation here. And now we need to find the value of this part, which we can call psi. I have no idea how to find the value of this. Wait, that's so cool. Thank you, mathematical object. Do you think we can prove this right now?
No, looks too difficult. In any case, we can rewrite the right-hand side like this and then substitute psi.
It's much easier now. We can separate the purely rational parts of the integrand and then solve them. Then, if we substitute u equals 1 over x in the first equation, we can combine the two. Now here's a punchline. If we replace every s with 1 minus s, the right-hand side stays the same. Therefore, these two halves are equal.
This can also be written as this, which I don't really have the time to explain.
Are we like 3 minutes into the video?
Fine, here's a treat. Anyways, when does zeta of s equal 0?
Well, obviously, if you let s be a negative even integer, and it has to be negative or else this would be undefined, then sine of pi s over 2 would equal to 0. So zeta of s would be 0.
Those are known as the trivial zeros.
Other than that, everything else can't be 0, so the only other option is zeta of 1 minus s is equal to 0. In other words, if there's a 0 of this side of the line re of s equals 1/2, then there must be a 0 on the other half.
We call this line the critical line. Wouldn't it be nice if all roots lie on this line? That is what Riemann's hypothesis is. Do all non-trivial zeros of the Riemann zeta function have a real part of 1/2?
So, how is it important?
Well, remember how I said that the zeta function is equal to this infinite product? Well, if you take the logarithm of that, you end up with this. Now here's an integral. Evaluating it, we can see that it's equal to n over s, so replacing them, we get whatever this is. Now here's where the prime counting function comes into play. For each point, what do we have to multiply it by?
For the first integral, we add another x to the minus s minus 1 for each p such that p is less than or equal to n. For the second interval, it's the same. It adds half whenever it's greater than or equal to p squared. Same goes for the others, so the answer is this.
We denote this function with capital Pi. Also, a bit of a nitpick, we're actually using a variation of the function where it takes the average of the two limits whenever there's a discontinuity, just for a semblance of continuity. So yeah, the zeta function and the prime counting function are related. With about 3 more pages of manipulation, Riemann eventually devises this formula for capital Pi.
What's the function Li of x?
The integral of 1 over log t
And the rho?
over non-trivial zeros of zeta.
Ah, so that's why finding these zeros is important. We can use it to predict prime to some extent.
I'd say so. If the Riemann hypothesis is true, then the difference between pi and Li is O of square root of x log of x. Also, there's a generalized Riemann hypothesis that shows it for this function, where chi of s satisfies multiplicativity and periodicity. Hardy and Little introduced it to show that if it's true, primes of the form 4n plus 3 become more common of primes of the form 4n plus 1 to some extent. For now, this $1 million question remains open and ready for someone to prove it, or disprove it. And by $1 million question, of course we mean literally, because it's one of the Millennium Problems introduced in 2000 by the Clay Mathematics Institute.
You can actually get cash money if you prove it, so go ahead. Actually, please don't, for your own sanity.
Now, Sayo, let's see what that last challenge is.